Okay, so now we're going to go and look at the fast Fourier transform, the FFT, and try and understand how that's about and how it connects to the discrete Fourier transform and to the continuous Fourier transform as well. Okay, so let's just start out with the Fourier series. Because the FFT is really about the Fourier series. It's certainly the easiest way to think about it. So we're on a finite interval from minus L to L. And we assume that we can write our function as the sum of it's a Fourier series. And we write it in terms of the complex Fourier series rather than sines and cosines. Now this is just a better idea to use the complex Fourier series. It always is better. There's never a time when it's better to use sines and cosines actually, but it's just a bit, when you first meet it, it'll be a bit confusing if you get to, complex numbers and all that stuff. Okay, and Kn is equal to the periodic things. Because the Fourier series really lives on the unit circle. And the Fourier series is really about power series and all kinds of stuff. They're very, very much tied up with complex analysis, because on the unit circle, this is powers of z. All right, but forgetting all that, there's our expansion, and we substitute that into the diffusion equation. So our diffusion equation is dtc is d dx squared c. So we substitute that into this, we substitute this expansion for c, and we end up with this expression here. Sum n equals minus infinity to infinity of time derivative of c n hat e to the I k n x is equal to the sum of, okay, and then we differentiate with respect to x twice, which of course is going to give us the minus k squared. And we have to add in a d as well. Let's put it in a rather funny place because there isn't a space for it. Alright, so there's our expression here, and we can see here from the orthogonality of the Fourier series that each individual term must be true, must be equal. So the time derivative of c n hat must equal minus k squared d c n hat. Okay, so we can immediately solve that. It's amazing how often these very simple DEs appear. Times Cn naught, whatever the initial value of Cn at naught, Cn hat at 0. Alright. So there's our solution to this equation, and we can substitute that back into here and we get an expression for Cn of x. So it's the sum from n equals minus infinity to infinity of e to the minus k squared dt Cn naught hat times e to the I k n x. Kn is just this multiple of pi here, so it's just a notation. I could have put n pi over L or something. And finally, we can calculate what Cn naught is equal to also from our Fourier series, right? Cn naught is equal to 1 over 2L, the integral from minus L to L of e to the minus I kn. Now anything that's in plus I becomes minus I here. Okay, and that's C naught of x dx. Okay, so that's just the Fourier series solution to this equation, so assuming that and this actually solves this diffusion equation with periodic boundary conditions, and we're going to use the periodic boundary conditions. We're going to make L big enough that L big enough we can go from minus infinity to infinity. So we haven't really talked about the fast Fourier transform at all. We've just done the Fourier series expansion and we've solved this equation here, okay? From the initial, just doing a Fourier series solution of this equation.